magnification for a spherical mirror. So there are three different types of magnification, which are transverse or lateral or linear magnification. Second is longitudinal magnification, and third is superficial magnification. So first we will learn about transverse or lateral or linear magnification. In this figure you can see AB is the object and small ab is the image produced by a concave mirror. So linear magnification is the ratio of the image height to the object height. If I consider the height of the image is h1 and the height of the object is h2, then linear magnification equals to height of the image by height of the object. Here height of the image is h1 and it is in downward direction, so according to our sign convention the height is negative, so minus h1 by height of the object, so object in the upward direction, so plus h2, so minus of h1 or h2. This is the linear magnification in this case. So here this minus sign signify one thing, that is the image is inverted by nature. Here if linear magnification m, if we take the magnitude of m, it becomes greater than 1, then we can say the image is magnified, and if the value of m is less than 0, then we can say the image is inverted, and if m greater than 0, then image is erect. So these are the conditions of the nature of images. Next, we already know that the ratio of height of the image to the height of the object is equals to the distance of the image to the distance of the object. So let's try to understand from where this relation comes. From triangle ABP and from triangle ABP, that is this large triangle and this small triangle, these angles are 90 degree. Angle A equals to angle A equals to 90 degree. Now this is the angle of incidence theta and this is the angle of reflection. So the both angles are same. Angle BPA equals to angle BPA from laws of reflection. These two angles are same, so angle B and angle B will also become equal. So angle B is equals to angle B. So triangle ABP and triangle ABP are similar. So we can write AB by AB equals to PA by PA. So here AB is the height of object, AB the height of image equals to PA object distance this is image distance. So we can reverse it, that is height of the image by height of the object equals to image distance by object distance. So from this condition we can derive the conclusion that linear magnification equals to height of the image by height of the object also equals to image distance by object distance. We know in case of mirror 1 by v plus 1 by u equals to 1 by f. This is the relation between image distance, object distance and focal length of a spherical mirror. Here if we multiply the both side by v by v plus v by u equals to v by f. So v by v 1 plus v by u represent the linear magnification m equals to v by f, or m equals to v minus f by f. So this is the linear magnification in terms of image distance and focal length of the spherical mirror. Again 1 by v plus 1 by u equals to 1 by f. Now if I multiply the both side with u by v plus u by u equals to u by f, or u by v represents 1 by m plus 1 equals to u by f. So 1 by m equals to u minus f by f, or m equals to f by u minus f. This is also the form of linear magnification in terms of object distance and focal length. So here this is the relation between linear magnification, image distance and focal length, and this is the relation between linear magnification, object distance and focal length for a spherical mirror. So these are the all things of linear magnification. So next, longitudinal magnification. So this is the type of magnification produced by a spherical mirror when an object is placed along the principal axis of that spherical mirror. If I consider my hand as a spherical mirror, so this is the principal axis. So if an object is placed in this way, that is parallel to the principal axis or along the direction of principal axis, then the magnification produced by that spherical mirror is defined as longitudinal magnification. So here let's consider this is the object, this is a large object. So let's consider this is the object, u1 is the distance of this point and u2 is the distance of the far point, and here this is the image and this distance is v1 and this is the distance of v2. So the image length is v2 minus v1 and the object length is u2 minus e1. So here the longitudinal magnification is defined as length of the image to the length of the object. So we can write longitudinal magnification equals to length of the image to the length of the object. So here length of the image is v2 minus v1, taking the magnitude. In case that v1 becomes greater than v2, then we will take only the positive value, and in this case u2 minus u1. This is the formula of longitudinal magnification. But in case of small object, the image will also become small. In this case, this v2 minus v1 is represented as dv and this u2 minus u1 is represented by du. So here the longitudinal magnification is defined as dv by du, and we know that 1 by v plus 1 by u equals to 1 by f. So differentiating both sides with respect to u, d du of 1 by v plus 1 by u equals to d du of 1 by f. So here d du of 1 by v plus d du of 1 by u equals to focal length of a spherical mirror is always remains constant. We know the differentiation of any constant term gives value 0. So here minus 1 by v square into dv du, it will become minus 1 by e square equals to 0. So here dv du equals to minus of v by u whole square. We know V by U defined the linear magnification, and dV du is defined as longitudinal or axial magnification. So axial magnification equals to minus of linear magnification square. So dV du equals to minus V by U square. So this is our longitudinal or axial magnification. You have to remember two things. For large object, we will apply this formula, the length of the image to the length of the object, and for small objects, we will consider this formula, that is differentiation of V with respect to U, which gives this formula. Here, superficial magnification is defined as the ratio of the area of image to the area of object. Superficial magnification equals to area of image by area of object. In this figure, let's consider this is the object, its length is A1 and breadth is P1. So area is A1 into V1, and this is the image produced by a spherical mirror of that object. So here the length of the image is A2, so area of the image is A2 into B2. So here we can write the superficial magnification equals to A2 B2 by A1 B1. Now let's consider the linear magnification of the edge. So we can write M equals to length of so we can write linear magnification M equals to length of the image by length of the object, that is A1, and again M equals to, we also can write the breadth of the image by breadth of the object. Now this is equation number 1, this is equation number 2. Multiplying 1 and 2, what we will get? M into M equals to A2 into B2 by A1 into B1, or A2 into B2 by A1 into B1 represents the superficial magnification. So superficial magnification M is equals to linear magnification square. So this is the relation between linear magnification and superficial magnification, and we also can find out the superficial magnification by this relation, that is the area of image by area of object.